In Table 7.2, Step 6, concerning feeder protection, the reason only 80 amps for the breaker capacity and 16 amps full load currents of one motor are included is because the feeder protection requirement is to protect the feeder from overcurrent and not necessarily the motors themselves. The largest breaker capacity that will provide adequate overcurrent protection for the feeder in this particular scenario is 80 amps. The sum of the full load currents of the other motors in that line is less than the 80 amps breaker capacity. Consequently, the other motor's 30.8 amps full load current is not included in the feeder protection calculation because it is not required to provide overcurrent protection for the feeder, given the existing 80 amps breaker capacity. Essentially, the feeder protection is sized to handle the overall load and potential overcurrent conditions on the feeder itself, and the individual motor protection is addressed separately. Now, let's shift our focus to page 296, figure 7.22. The values used in this figure are specifically based on the particular requirements of the electrical system that is being designed. It is important to understand that not all values are universally applicable or always used in every design scenario. For instance, if the electrical system in question does not incorporate a transformer, the transformer reactance, denoted as X subscript T, value would simply not be used in the calculations. Similarly, if the system does not include a capacitor bank, the capacitor reactance, denoted as X subscript C, value would not be necessary for the design calculations. The values of resistance, symbolized as R, and inductance, symbolized as L, are frequently utilized to calculate voltage drop and impedance within the electrical system. These parameters play a crucial role in understanding the behavior of the system under various load conditions. Conversely, the values of capacitance, symbolized as C, and resistance, symbolized as R, are typically employed to calculate power factor correction. Power factor correction is a technique used to improve the efficiency of the electrical system by minimizing reactive power. The specific values that are ultimately used in figure 7.22 will vary depending on the intricacies and requirements of the specific electrical system being designed. In essence, the engineer must carefully consider the components present in the system and the performance characteristics that are desired in order to select the appropriate values for the calculations. To further elaborate on the components and calculations, let's discuss the role of each parameter in more detail. Resistance, represented by R and measured in ohms, opposes the flow of current in a circuit. It is a fundamental property of all conductive materials. Inductance, represented by L and measured in henries, is the property of a circuit that opposes changes in current. It is primarily associated with coils and transformers. Capacitance, represented by C and measured in farads, is the ability of a circuit to store electrical energy. It is primarily associated with capacitors. Reactance, represented by X, is the opposition to the flow of alternating current due to inductance or capacitance. It is measured in ohms. Impedance, represented by Z, is the total opposition to the flow of alternating current in a circuit. It is the vector sum of resistance and reactance, also measured in ohms. Voltage drop is the decrease in voltage along a conductor or through a circuit element due to impedance. Power factor is the ratio of real power to apparent power in an alternating current circuit. It is a measure of the efficiency of the electrical system. Transformer reactance X subscript T represents the opposition to alternating current flow within the transformer. Capacitor reactance X subscript C represents the opposition to alternating current flow presented by the capacitor. When designing an electrical system, it is essential to consider all of these parameters in order to ensure that the system operates safely and efficiently. The engineer must select appropriate values for each component based on the specific requirements of the application. For example, the resistance of a conductor must be low enough to minimize voltage drop, while the impedance of a circuit must be high enough to limit short-circuit currents. Furthermore, it's also important to note the difference between full load current, or FLC, and lock rotor current, or LRC. Full load current is the current drawn by a motor when it is operating at its rated load and voltage. Locked rotor current is a current drawn by a motor when it is initially started and the rotor is not yet turning. Locked rotor current is typically much higher than full load current, often several times higher. This high inrush current can cause voltage dips and potentially damage the electrical system if it is not properly accounted for. Therefore, the electrical system must be designed to handle the locked rotor current of all motors connected to it. This is typically achieved by using appropriately sized conductors and overcurrent protection devices. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect the electrical system from excessive current flow. They are designed to trip or open the circuit when the current exceeds a certain threshold. The size of the overcurrent protection device must be carefully selected to protect the electrical system without causing nuisance tripping during normal operation. The National Electrical Code, or NEC, provides guidelines for selecting the appropriate size of overcurrent protection devices. The NEC contains numerous tables and articles that specify the requirements for various electrical installations. For example, NEC Table 430.52 provides guidance on selecting the appropriate size of overcurrent protection devices for motors. This table specifies the maximum allowable size of the overcurrent protection device based on the motor's full load current. NEC Article 430 covers the requirements for motors, motor circuits, and motor controllers. It provides detailed information on motor protection, motor control, and motor installation. When designing an electrical system, it is essential to comply with the requirements of the NEC. The NEC is a widely adopted standard that ensures the safety of electrical installations. Compliance with the NEC helps to minimize the risk of electrical shock, fire, and other hazards. In addition to the NEC, there may be other applicable standards and regulations that must be considered. These may include local codes, state codes, and federal regulations. It is the responsibility of the electrical engineer to ensure that the electrical system complies with all applicable requirements. To summarize, the design of an electrical system involves careful consideration of numerous parameters and requirements. The engineer must select appropriate components, perform necessary calculations, and comply with applicable standards and regulations. The goal is to create a system that operates safely, efficiently, and reliably. The use of appropriate software and tools can greatly assist in the design process. There are many software packages available that can help with tasks such as load flow analysis, short circuit analysis, and voltage drop calculations. These tools can save time and improve the accuracy of the design. Furthermore, ongoing maintenance and inspection of the electrical system are essential to ensure its continued safe and reliable operation. Regular inspections can help to identify potential problems before they become serious. Maintenance activities, such as cleaning and tightening connections, can help to prevent equipment failures. In conclusion, electrical system design is a complex and multifaceted process that requires a thorough understanding of electrical principles, standards, and regulations. By following established best practices and utilizing appropriate tools, engineers can create electrical systems that meet the needs of their clients while ensuring the safety of the public. Let's now consider some examples of how these principles apply in real-world scenarios. Firstly, consider a large industrial facility with numerous motors driving various pieces of equipment. In this case, the electrical system must be designed to handle the combined load of all the motors, as well as other loads such as lighting and heating. The engineer must carefully calculate the total demand load and select appropriately sized conductors, transformers, and overcurrent protection devices. The engineer must also consider the impact of motor starting on the electrical system. The high inrush current associated with motor starting can cause voltage dips and potentially damage sensitive equipment. To mitigate this risk, the engineer may use techniques such as reduced voltage starting or soft starters. Secondly, consider a commercial building with a mix of lighting, HVAC, and office equipment. In this case, the electrical system must be designed to provide reliable power to all the loads while minimizing energy consumption. The engineer may use energy-efficient lighting fixtures, variable frequency drivers for HVAC equipment, and power factor correction capacitors to improve the efficiency of the electrical system. The engineer must also consider the impact of harmonics on the electrical system. Harmonics are distortions in the voltage and current waveforms that can be caused by nonlinear loads such as electronic ballasts and variable frequency drives. Harmonics can cause overheating of equipment and interfere with the operation of sensitive electronics. To mitigate the effects of harmonics, the engineer may use harmonic filters. Thirdly, consider a residential building with a variety of appliances and electronic devices. In this case, the electrical system must be designed to provide safe and reliable power to all the loads while complying with the requirements of the NEC. The engineer must select appropriately sized conductors, overcurrent protection devices, and ground fault circuit interrupters to protect against electrical shock and fire hazards. The engineer must also consider the impact of renewable energy sources such as solar panels on the electrical system. Solar panels can generate electricity and feed it back into the grid. The electrical system must be designed to safely integrate the solar panels and prevent backfeeding into the grid during a power outage. To further delve into specific calculations, let's explore how to determine the appropriate conductor size for a motor circuit. The NEC provides guidelines for selecting conductor size based on the motor's full load current and the type of insulation used in the conductor. NEC Table 310.15 provides ampacity ratings for various types of conductors. The ampacity rating is the maximum amount of current that a conductor can carry safely without overheating. To determine the appropriate conductor size, the engineer must first determine the motor's full load current from the motor nameplate. Then, the engineer must select a conductor with an ampacity rating that is at least 125% of the motor's full load current. This is to account for the fact that motors may draw more than their rated full load current during starting and under certain load conditions. In addition to the ampacity requirement, the engineer must also consider the voltage drop in the conductor. Voltage drop is the decrease in voltage along the conductor due to its impedance. Excessive voltage drop can cause the motor to operate inefficiently and potentially damage the motor. The NEC recommends that the voltage drop in a motor circuit should not exceed 5%. To calculate the voltage drop, the engineer must know the conductor's length, resistance, and the amount of current flowing through the conductor. There are various online calculators and software tools available to help with voltage drop calculations. Once the voltage drop is calculated, the engineer can adjust the conductor size if necessary to ensure that the voltage drop is within the acceptable limit. It's crucial to consult the latest edition of the NEC and any applicable local codes when designing electrical systems. The NEC is updated every 3 years, and it's important to stay current with the latest changes. Local codes may also have additional requirements that must be followed. By carefully considering all of these factors, electrical engineers can design safe, reliable, and efficient electrical systems.